Okay, let's dive into a deep scientific mystery, one that's been bugging computer scientists for decades. We're talking about why some problems are so incredibly hard that even our most powerful computers just give up. It's a story about a hidden structure and logic, and a wild new idea that might finally crack the case. So this is really the big question, right? You and I, we rely on computers for pretty much everything. But there's this whole class of problems where even the fastest machines on the planet just grind to a halt. What is it about them that makes them so fundamentally tough? Here's a perfect example, the traveling salesperson problem. Sounds simple, doesn't it? Just figure out the shortest loop that hits every city on a list. But here's the kicker. As you add more cities, the number of possible routes just explodes. It gets so big, so fast, that finding the absolute best one becomes basically impossible. And get this isn't some new puzzle. For over half a century, some of the smartest people in a field called computational complexity theory have been banging their heads against this wall, trying to prove why these problems are so hard. And for 50 years, they've been stuck. But what if the reason they're stuck is because they've been coming at it from completely the wrong direction? There's a new approach that's, well, it's flipping the entire mathematical script right on its head. To find the answer, researchers had to get a little weird and dive into something called meta-mathematics. So instead of just doing math, they started studying the rules of math. They looked at the fundamental assumptions, they're called axioms, that all of logic is built on. This is the absolute bedrock. Think of it like a game of chess. Normally, you start with the axioms, the rules for how a bishop or a knight can move. Then, you use those rules to prove a theorem, which is like working your way towards a checkmate. But reverse mathematics does the exact opposite. You start with the checkmate, the theorem, and you work backwards to figure out what's the absolute bare minimum set of rules or axioms that I need to make this outcome happen. It's a total reversal. So how does this radical, backwards approach actually work out in the real world? Well, it all starts by connecting two things that sound like they have absolutely nothing to do with each other: pigeons and secret codes. First up, the pigeons. The pigeonhole principle is one of those ideas that's so obvious it's almost funny. It just says that if you have, say, 10 pigeons but only 9 boxes to put them in, at least one box has to have more than one pigeon. Simple, right? But believe me, this simple idea is a powerhouse in mathematics. Now for the secret codes. Picture this. You and a friend each have a massive string of ones and zeros, and you need to figure out if your strings are identical without sending the whole thing back and forth. How do you do it with the least amount of communication? Well, for decades, every proof for the best solution to this problem relied on that same pigeonhole principle. And this is where the breakthrough happens. In the summer of 2022, a researcher named Jichen started wondering, what if we could work backward? Could the secret code problem actually prove the pigeon principle? By December, he and his collaborator Jichen Li had their answer, a definitive yes. The two ideas weren't just connected, they were two different ways of saying the exact same fundamental truth. And at first discovery, it wasn't just a single connection. It was like pulling on one loose thread and realizing it was part of a giant, invisible web. I love how the researcher Li Jichen put it. He said, what started as a simple pair of connected ideas just exploded. Using this reverse mathematics approach, they started finding all these shocking, hidden connections all over computer science. So they had their first big win. Pigeons and secret codes were basically two sides of the same logical coin. But that, it turns out, was just the warm-up act. Next, they pointed their new tool at a totally different corner of the field: the palindrome problem. A palindrome is something that reads the same forwards and backwards, like race car. For a computer, the problem is figuring out how to check if a huge string of numbers is a palindrome in the most efficient way. And this led them to their most jaw-dropping discovery yet. They proved that the simple, obvious truth about pigeons is logically, fundamentally, the exact same thing as the complex problem of a computer identifying a palindrome. This connection was so out of left field that even Li Jichen said he wouldn't have believed it. It just sounds ridiculous. I mean, on the surface, what could these two things possibly have in common? One's about counting, the other's about computation. So what does a ridiculous connection like this really mean? It suggests that the reason these computer problems are so hard isn't just a matter of processing power or clever programming. Their difficulty is woven into the very fabric of logic itself. It's as fundamental as counting. Okay, so let's zoom out and look at the big picture. What does this new map of hidden connections tell us about why we've been stuck on these hard problems for over 50 years? Well, this new web does a few huge things. First, it shows us the limits of our mathematical tools. Second, it proves that a whole bunch of different problems are secretly just the same puzzle wearing different costumes. It gives us a brand new map for the whole field. And maybe most importantly, it finally helps explain why we've been stuck. Everybody was trying to solve the same deep puzzle, they just didn't know it. This quote from another theorist, Marco Carmesino, just says it all, doesn't it? There's this new feeling in the air. After decades of hitting a wall, there's a real energy to step back, look at the very foundations, and start building again on something solid. This whole journey just leaves you with this incredible thought. I mean, if a simple truth about counting pigeons is deeply, secretly connected to a computer recognizing a palindrome, it really makes you wonder, what other profound hidden connections are out there, just waiting to be found? Not just in computers, but in all of science.